Welcome to Theorem 10, which uses mathematical language to describe why 3 points will have a unique circle drawn through them. Theorem 10 says that any 3 non-collinear points, meaning not in a straight line, are on a unique circle whose center is the point of concurrency of the perpendicular bisectors of the intervals joining them. Huh? What does that even mean? Well, let me try. If we take any 3 points not in a straight line, and we find their center, then there is a unique circle that will pass through all 3 of those points. But point of concurrency of perpendicular bisectors, what? Look, don't panic. A bisector is just a line that cuts another one in half. A perpendicular bisector will just cut another line in half, but at 90 degrees. So if we join BC and draw another perpendicular bisector, and do the same with AC, they should all cross at one point in the middle. So what's a point of concurrency? Well, that's just the point where the 3 lines meet, and this happens to be the center of the circle. This is a method for finding the center of a circle knowing 3 points, so let's look at a proof behind this. Setting up our proof, we begin by stating that we want to prove that there is only one circle through A, B, and C whose center is the point of concurrency of the perpendicular bisectors of AB, BC, and CA. We know there are 3 points, A, B, and C, that are collinear. We need to join AB and BC in our construction. We then construct the perpendicular bisector of AB, BC, knowing that D is the midpoint of AB and E is the midpoint of BC. Lastly, F is their intersection. AB and BC are not in a straight line. This is important to state because if they were, the perpendicular bisectors wouldn't intersect. In this case, they have to cross at F. DF is the perpendicular bisector of AB, which means that all the points on DF are the same distance from A and B. So AF is going to equal BF. Similarly, because EF is the perpendicular bisector of BC, all points on EF are the same distance from B and C, and this means that BF has to equal CF as well. I just removed the aim, the given, and the construction working out just to make room for the rest of my proof. Okay. I now go on to say that F is the only point that is the same distance from A, B, and C. I also say that the perpendicular bisector of AC also has to pass through F because the perpendicular bisector of a chord passes through the center. Therefore, there is only one circle through A, B, and C whose center is the point of concurrency of those perpendicular bisectors of AB, BC, and CA. This was a long proof and not used often. What I'd like you to take from this video is the language used, like perpendicular bisector and point of concurrency, as well as a method on how to find the center of a circle which passes through any 3 points. The next video will be on angles in a circle, looking at angles in the same segment as well as angles in a semicircle. Thanks for watching.